Children, today we are going to discuss the splitting of d orbitals in octahedral, tetrahedral, and square planar fields. Myself, Dr. Digna Varghese, we are considering the splitting of d orbitals in octahedral field. We know there are 5 d orbitals, that is dxy, dxz, dyz, dx square, y square, and dz square. Here you can see two d orbitals, that is dz square and dx square y square. In the case of dz square, it has a maximum amplitude along the z axis and there is a donut in xy plane. In the case of dx square y square orbital, it has a maximum amplitude along x and y axis. We are moving to the shape of other three d orbitals. Here you can see dyz orbital, dxz orbital and dxy orbital. In the case of dyz, it has a maximum amplitude 45 degree to the y and z axis. In the case of dxz orbital, it has a maximum amplitude 45 degree to the x and z axis. For dxy orbital, it has a maximum amplitude 45 degree to the x and y axis. These orbitals are not along the axis, like dx square, y square orbital or dz square orbital. It is in between the axis. That means dyz orbital is in between the y and z axis. For dxz orbital is in between the x and z axis. Similarly, dxy orbital is in between the x and y axis. So these orbital has a maximum amplitude 45 degree to the corresponding axis. The orientation of the lobes of the orbitals with respect to the coordinates of the d orbitals. The d orbitals are again divided into two groups, that is axial orbitals and non-axial orbitals. Axial orbitals are dx square y square and dz square orbitals. We know in these orbitals the lobes of the orbitals are along the axis, that is dx square y square is along the x and y axis and dz square along the z axis, and the lobes there is a donut that is along the xy plane. Okay, according to the group theory, the axial orbitals are again called EG orbital, in which the two orbitals are doubly degenerate. Another one is non-axial orbitals. Non-axial orbitals are those orbitals in which the lobes of the orbitals are lying in between the axes. Non-axial orbitals are dxy, dxz and dyz orbitals, in which you can see here the lobes are in between the corresponding two axes. According to the group theory, the non-axial orbitals are also known as T2G orbitals. That means triply degenerate orbitals. Triply degenerate orbitals. We are dealing with the splitting of d orbitals in octahedral field. Before that, we are considering the case of free metal ion. Here you can see for the free metal ion, the 5 d orbitals are degenerate. We know the 5 d orbitals in a free metal ion are degenerate. That means it has the same energy. Now we are going to the octahedral complex. Consider an octahedral complex Ml6N plus. Set general formula. M represents the central metal ion and L is the point negative charge, that is ligands. Here is 6 ligands. So it is geometry is octahedral. The center metal cation Mn plus is placed at the center of the octahedron. Mn plus is surrounded by 6 ligands, 1, 2, 3, 4, 5 and 6. So it is an octahedron. In the octahedral field, also approaching the metal ion through the axis, that you can see here, the ligands approaching the metal ion through the x, y and z axis. That is, the ligands are placed in the corners of the octahedron. Okay, now we are considering what happens to the axial orbitals when the ligands are approaching to the metal ion. Here you can see the three axes x, y and z axis which point along the corners that we have already seen. The 6 ligands, 1 here, 2 here, 3, 4, 5th and 6th ligands surrounded the metal ions are pointing along the corners, that is along the 3 axes. What about the axial orbitals when the ligands approaches to the axial orbitals? Here you can see the axial orbitals dx square y square. That means the lobes of the orbital is along the x and y axis. The ligands are approaching through x, y axis. So the ligands and the lobes of the d orbitals here, that is dx square y square, are in the same direction. So electrons from the ligand and electrons from the metal ion causing a large repulsion here. Therefore, these ligands approaching the metal ion through the axis can cause a large destabilization to the axial dx square y square orbitals. Okay, in the same way as the case of another axial orbital that we know, dz square orbital, in which the lobes are in the z direction and there is a donut in the xy plane. So the ligands along the x, y and z axis can approaches the lobes of the d orbitals here, and that can cause a large destabilization to the dz square orbital. These dx square y square and dz square orbitals are destabilized and in the same amount of destabilization by the ligands. Okay, so these axial orbitals, that is dx square y square and dz square orbitals, are doubly degenerate. Okay, that means according to group theory, these axial orbitals are also known as EG orbitals, that is doubly degenerate orbitals. Now we are considering the non-axial orbitals, that is dxz, dyz and dxy orbitals. We know dxz orbitals has a maximum amplitude 45 degree to the x and z axis. Dyz orbitals has a maximum amplitude 45 degree to the y and z axis. And likewise, the dxy orbitals has the maximum amplitude 45 degree to the x and y axis. Here you can see the metal d orbitals are in between the axes. We know the ligands are approaching through the axis to the central metal ion that you can see from this figure. So the non-axial orbitals are not placed along the axis. So they are not directly attached or approaching towards the ligands. Okay, they are in between the axis. So in the case of non-axial orbitals, the ligands are not directly approaching to the lobes of the orbitals. Okay, so these orbitals are somewhat stabilized by the six ligands as in the case of axial orbitals. We know axial orbitals are highly destabilized because of electrons from the ligand and the electrons from the metal ion are directly approaching. So there is a large repulsion. But in the case of non-axial orbitals, here you can see d XZ orbitals. The XZ orbitals are lying in between the X and Z axis. So the ligands approaching through the X, Y and Z axis. So these orbitals are no direct contact with the ligands. So there is somewhat less repulsion occurs compared to the case of axial orbitals. Okay, children. So here is stabilization from the axial orbitals occurs by these six ligands. So they are in the stabilization is the same amount for the non-axial orbitals. So we can say that these are in the degenerate state or triply degenerate state. According to group theory, the non-axial orbitals are also known as T2G orbitals. Now we are going to study the energy level diagram for an octahedral complex. Now we are considering a special case in which all the ligands are approaching to the central metal ion are at an equal distance from each of the metal d orbitals. That is, the ligand field, we can call it as a spherically symmetrical field. The energy of each of the d orbitals will be the same by the six ligands that are approaching to the metal ion from a equal distance. Okay, but this is only a hypothetical situation. It is also known as barycenter. Once again, I will tell you, for a free metal ion, all the d orbitals are in a degenerate state, but its energy is lower. Now we are considering a case in which all the ligands are approaching to the central metal ion with a equal distance. Okay. So these ligands approaching to the metal ion equally. So again the d orbitals are in a degenerate state, but their energy or average energy of the d orbitals with the ligands increases. This type of crystal field is known as spherical crystal field. But this we know it is an only hypothetical situation. The actual case of an octahedral complex that we can see here, the ligands approaching towards the metal ion in the axial orbitals. What are the axial orbitals? That is the x square, y square and dz square orbitals that are lie directly in the path of the ligands and experiences a greater repulsion than the other three non-axial orbitals whose lobes are directed in between the path of the approaching ligands. So non-axial ligands, that is T2G orbitals, the energy of the T2G orbital is decreased while the energy of the EG orbital is increased. If greater repulsion, greater is the energy of the orbitals. Therefore, the T2G level is triply degenerate and of lower in energy, and EG level, that is doubly degenerated, of higher in energy. The degeneracy of the 5d orbitals is removed under the influence of the ligands. Okay, that is the basis of crystal field theory. That means the splitting of d orbital is the basis of crystal field theory. The separation of the 5d orbitals of the metal ion into two sets, that is T2G level and EG level, having different energy, that is called crystal field splitting or energy level splitting. This concept of crystal field splitting makes the basis of crystal field theory. So the heart of crystal field theory is that the splitting of d orbitals. The summary of the crystal field splitting in an octahedral field is that consider a complex ML6 when the ligands are approaching to the central metal ion, the d orbitals which are directed towards the cation, ligands, that is EG orbitals, are more cause repulsion and they are having higher energy when compared to the orbitals that are not directly attached to the or approached to the ligands. They have lower in energy. That means T2G have lower in energy. That means these orbitals are stabilized somewhat more than the EG orbitals. EG orbitals are along the axis, so these have higher energy or large repulsion and more destabilization. So they have higher in energy. You can see an energy gap between T2G and EG level or orbitals, that is known as octahedral field crystal field splitting energy or simply crystal field splitting energy, that is represented here by delta O. O represents for octahedral field. So non-axial orbitals T2G orbitals are lost energy by minus 0.4 delta O, while axial orbitals, that is EG orbitals, gain energy by plus 0.6 delta O. Okay, or plus 0.6 delta O or plus 3 by 5 delta O. So EG orbitals are destabilized, whereas T2G orbitals are somewhat stabilized by minus 0.4 delta O. So delta O is the overall splitting between the EG and T2G orbitals. That is also known as octahedral field splitting energy. O in delta O is 4 octahedral. Energy level diagram for an octahedral field. Going to study the splitting of d orbitals in a tetragonal field. You can see here an octahedral complex structure. If the two trans ligands in an octahedral complex, that is on the z-axis of an octahedron, are moved away from the central metal cation. So the distance between the metal ligand on z-axis increases. The distance of the two ligands on z-axis from the metal cation is slightly greater than the other four ligands in the xy plane. Okay. Such type of distortion in an octahedral complex known as tetragonally distorted octahedron or simply tetragonal structure. We know the d orbitals along the z-axis, that is dz square, dxz and dyz orbitals experience a less repulsion because splitting due to the repulsion between the electrons from ligands and metals. Here the ligands are moving from the metal ion, so the distance increases. So the electron interaction between the metal and the ligand decreases. So there is less repulsion when compared to xy plane ligands. Okay, that is dx square y and dx square y square orbital. So the electrons or orbitals along the z-axis experience a less repulsion. That means it has a less energy compared to orbitals in the xy plane. Okay. Considering this splitting of d orbitals in a tetragonal structure, the more convenient way to express the splitting of d orbitals in tetragonal structure by starting with the splitting in octahedral complex. That you can see here, the energy 5 d orbitals are in a degenerate way when the ligands are approaching in a spherical field or spherically symmetrical field. When the ligands, but the actual case, the ligands are approaching along the axis. So the d orbitals are splitting like this into two sets, T2g sets and EG sets that you can see here. But in a tetragonal geometry, the distance of the two ligands along the z-axis are moved away from the central metal ion or removing them away, but actual case is not like that, not removing them completely from the metal ion, only increasing the distance between the metal and the ligand. So the ligands along the z-axis can cause some influence on the metal d orbitals along the z-axis. Okay. Therefore, the d orbitals along the z-axis and in that is dxy, dxz and dyz and dz square orbitals cause less repulsion. So it has less energy than the ligands in the xy plane. So here you can see the T2g sets split into again into two, that is the ligands with z-axis component having lesser energy than the d orbitals in xy plane. So dxz and dyz orbitals have less energy than the dxy orbitals, and here in the case of Eg orbitals, the dz square orbitals have less energy when compared to dx square y square orbitals. So this means that the ligands along the z-axis can cause a less repulsion to the between the d electrons and the ligand electrons, because the metal ligand distance is increased here, so that the electrons containing orbitals, d orbitals along the z-axis have less repulsion. That orbital experience a less repulsion from the ligands. Okay, while the orbitals in the xy plane experiences a relatively high or greater repulsion, therefore their energy is increased. So, splitting of d orbitals in a tetragonal field is in this way. The energy of the d orbitals in a tetragonal complex under the influence of the ligands dxz and dyz has the same energy, that is, they are doubly degenerate here, and dxy is somewhat higher energy, and dz square is higher energy, and dx square y square is the greater energy. So the order of energy for the d orbital is dx square y square is greater than dz square greater than dxy greater than dxz dyz orbitals. The orbitals in square planar field. If the two transligands on the octahedral geometry, that is along the z-axis, the ligands are completely removed here. So it forms a square planar geometry. It can cause rise in the energies of the dxy and dx square y square orbitals, because in along z-axis there is no ligands, so there is no electron-electron repulsion. Therefore, the orbitals having z component have lower in energy compared to the other orbitals in xy plane. So fall in the energies of dxz, dyz and dz square orbitals. So energy of the different d orbitals in a square planar field is like this dxz, which is equal to dyz, that is they have same energy, which is lesser than the dz square orbitals, which is lesser than the dxy orbitals, and it is again less energy than the dx square y square orbitals, because in the xy plane the ligands are there, and between metal and the ligand electrons there is greater repulsion. Okay, so greater is the repulsion, greater is the energy. Splitting of d orbitals in square planar complex. Crystal field splitting in square planar complex is shown here, and the splitting is denoted by delta Sp, where Sp is the square planar, which represents the total square planar splitting from the lowest dyz dxz to higher dx square y square orbital. Okay, so delta Sp is equal to the sum of three delta values, that is delta 1 plus delta 2 plus delta 3. Delta 1 is the energy difference between the dxy and to the dx square y square orbital, and delta 2 is the energy difference between the dz square and dxy orbitals, and delta 3 represents the energy difference between the dxz dyz to the dz square orbitals. Okay, so in a square planar complex, delta Sp is the sum of delta 1 plus delta 2 plus delta 3. It has been found that the value of delta Sp is larger than the crystal field splitting in octahedral field. Okay, this is because of the reason that the dxz, dyz orbitals interact only with two ligands in the case of square planar complex, whereas in octahedral complex, the delta xy, delta xyz orbitals interact with the four ligands. Okay, so delta Sp is equal to 1.3 delta O. Splitting of d orbitals in a tetrahedral field. Here you can see a tetrahedral complex. A convenient way to express the tetrahedral splitting, that means a convenient picture of a tetrahedron which is placed inside a cube. Okay. The center of the cube is also or the same as the center of the tetrahedron at which the central metal ion is placed. Okay. Here Mn plus is the center of the tetrahedron and also for the cube. The four corners of the tetrahedron, one is here and one is here and one is here and one is here, with, at which the ligands are placed. These four ligands lying between the three axes. We can see here the axis represented in blue lines, x-axis, y-axis and z-axis. The ligands are approaching the alternate corners of the cube, or the ligands placed on the corners of a tetrahedron. And these ligands are lying in between the axes x, y and z axis. These axes are go through the center of the cube. Considering what happens to the orbitals in the central metal ion. The lobes of the dxy, dxz and dyz orbitals, that is T2 orbitals, are lying between the axes. That is, they are lying directly in the path of the ligands. These will experience a greater force of repulsion. Here you can see the non-axial orbitals. The non-axial orbitals, that is dyz, dxz, dxy, that is actually placed in between their lobes are placed in between the axes. Okay, so these are lying between the axes. Here the ligands are also approaching to the metal ion in the not along the axis but in between the axes. So these orbitals, these non-axial orbitals and these ligands are in the same direction. So the electrons of these non-axial orbitals of the metal and the electrons of the ligands will experience a greater force of repulsion. So they have higher energy. Okay. The dz square and dx square y square orbitals whose lobes are lying along the axis. So they are along the axis, that is at the center of the tetrahedron or the cube here. Okay. So they are not directly approaching to the ligands. So the electrons in these orbitals and ligand electrons cause less repulsion. So they are energy of these orbitals is decreased. So energy of the T2 orbitals and is increased due to the greater repulsion. Energy of the E orbitals is decreased here due to less repulsion. T2 means triply orbital degenerate orbitals in the tetrahedral field. Here center of symmetry is absent. So the term G is removed here, and in the case of E orbitals, that is doubly degenerate orbitals. Splitting of d orbitals in tetrahedral field. Crystal field splitting in tetrahedral field is diagram is shown here. Delta T represents the crystal field splitting in tetrahedral field, and T means tetrahedral field. Here the 5 d orbitals are splitted into two sets, that is E sets, that is dx square y square and dz square, having lower energy. dxy, dxz and dyz orbitals has higher energy, that is T2 sets, and the energy difference is given here, that is delta T. Energy difference from the barycenter to E orbitals, that is minus 6 dq, and energy level difference to from barycenter to triply degenerate sets, that is plus 4 dq. So these orbitals have lower energy and these orbitals have higher energy. Okay. Delta T, which is equal to 4 by 9 delta O. This means that it is smaller than the splitting in octahedral field. This is because there are only 2 by thirds of the ligands and there are only less direct effect on the ligands when compared to octahedral complexes. Crystal field stabilization energy of tetrahedral complexes are not large enough to force the electrons to pair, or low spin, and low spin complexes are rarely observed. That means in the case of D6 configuration, the electrons 1, 2, before pairing it is going to the higher energy level, that is T2 level, and after that pairing takes place. So low spin complex formation is rarely observed. In the case of tetrahedral complexes, they are always high spin complexes, or they form high spin complexes. By this, I conclude here. Thank you.